next speaker is Dr. Samuel Davenport. He is currently a research fellow from UC San Diego. Okay, let's welcome Dr. Davenport.
Hi guys, thanks for coming. Today I'm going to be talking about our work on Localized Cluster Enhancement, TFCE revisited with valid error control. And this is joint work with Wouter Wieder and Jelle Goeman from the Netherlands. So just to give an overview of TFCE, the kind of setting we're in is that we assume that we have a test statistic at every voxel in the brain. Then TFCE is a widely used method to identify activation, and right now has over 5,000 citations. What it does is that it transforms a test statistic voxel-wise via some integral. And to understand this slightly better, it's easiest to look at a picture. So you can see from this picture that at a given voxel V, the transformation depends on basically this pink region and the extent in that peak region. And that means that at a voxel V, it basically borrows information from other parts of the brain, or in this case, just the 1D brain. So in practice, default parameters, h equals 2, e equals 0.5, and h0 equals 0 are chosen. Permuted TFCE statistics are calculated, and a cutoff T star which is based on the 95% quantile of the permutation distribution of the maximum, is chosen, and you would reject voxels V, for which the TFCE statistic exceeds the cutoff T star. Now, to give an example of that in practice, so here's an example where you apply TFCE to 20 subjects from the HCP. We get the following thresholded map. What we can reasonably ask the question is, in this map, if we see activation in a specific place, is there really activation there? Unfortunately, the answer is sometimes no. So really, as I mentioned before, TFCE can borrow information from all across the brain, across its support. So if we plot the support of the TFCE statistic, we see that from one part of the brain is very connected to the other, meaning that if you see significant activation in this part of the brain, it could be coming from another part. What that means is that TFCE can be used to make a global statement about the activation, but it struggles to localize the activation at a specific point. You can understand this a little better from a simple simulation. So here we have a true signal shown in yellow, and we basically generate 50 random images centered at this signal and calculate a voxel-wise T statistic, which is shown on the right. We calculate the TFCE transformation, and then we apply permutation testing to generate this cutoff T star and do a threshold. And you can probably see that in this example, there's immediately some sort of issue, right? Instead of finding a single cluster, we've actually found two. And the second one doesn't overlap with the original signal at all, so it's a false cluster. And it occurs basically because the TFCE statistic in that area is borrowing information from the true signal. And you can see that if we add in the support image, like we did before with the brain. So here, there's basically the TFCE statistic in that area is integrating information from the whole image. Instead, an alternative approach, cluster size inference, if you apply it to this data set, finds a single cluster, which is doing the right thing. So that was just one simulation, but we did many simulations to check the error rate. So if you look at the voxel-wise error rate, then TFCE can have a voxel-wise error of up to 80, 90%. But then so can cluster size. Cluster size is less than TFCE, admittedly, but it still can be inflated. That's because neither of these methods is really designed to be a voxel-wise approach. Instead, we can look at the cluster-wise error rate. So if we look at the cluster-wise error rate, that's really the probability of seeing a false cluster like this one here. If we look at the cluster size error rate, we can see in certain simulations that the cluster-wise error of TFCE can be inflated of up to like 30, 40%. Whereas instead, for cluster size inference, or cluster extent inference as it's also known, the error rate is below the nominal level. So TFCE was originally introduced in order to improve on cluster size inference. However, it doesn't control cluster error rates. A second major motivation for TFCE was to reduce researcher degrees of freedom, to make it threshold free. That's what the TF stands for. However, TFCE actually very much depends on a threshold H0, because we can see that the H0 depends how it borrows support from the rest of the brain. So how can we improve this? Well, we introduce a localized cluster enhancement. Localized because it's going to allow us to basically say that there's activation in a specific area of the brain. And cluster enhancement, basically we've dropped the TF because in our view, it's not threshold free. To do that, we calculate a test statistic, a regional test statistic for any region R in the brain, which is obtained by basically masking out the rest of the brain, calculating the TFCE statistic on that specific region, and then comparing the maximum of that regional test statistic to the original cutoff T star. We use the original cutoff, meaning there's no additional permutation required, other than the original one used in the default TFCE approach. So to understand that, we look at an example where we have 20 subjects. So here we have the test statistic map of 20 subjects. And then if we look at a region in the brain, here we have the middle frontal gyrus, and we apply a localized TFCE approach for that region. What that involves is masking out the rest of the brain, and then looking at the original test statistic only within that region, computing TFCE, but just within that region, so not having any influence from the rest of the brain, computing the maximum regional test statistic, and comparing that to the threshold, or to the cutoff T star. So what are the advantages of this approach? Well, essentially, if that regional TFCE is greater than the cutoff T star, then this localized cluster enhancement is able to make the claim that there is at least one active voxel within the region R. Now, this is provably valid with an error rate of 5%, and this is simultaneously over all regions R. What that means is that localized cluster enhancement is able to make specific regional claims that this part of the brain is active, rather than saying more global claim like TFCE. The fact that the simultaneity over all regions R means that this approach can be applied to either predefined regions based on some atlas, like the Harvard-Oxford or something else, or also to data-driven regions, such as clusters. And it's valid over all simultaneously, so you could do both at the same time. What this allows is it allows the user to explore the data and find the regions of interest that they like. So they can just choose the region, choose one region, check that, choose another region, check that, and it's all valid with a total error rate simultaneous of 5%. So here's an example where we look at 20 subjects from the HCP. This is one of the social contrasts. And if we apply this approach with the threshold H0 equals 0, then we find the following regions of activation, which is significant. What it means is within each one of these given regions, we can say within that region there is some activation, instead of which gives a much more local statement than TFCE would. And however, this also makes us think about, well, is H0 equals 0 really the optimal choice of the threshold? The answer is really no. So if we change that H0, we change it to H0 equals 3.1. Now this is the default threshold used in cluster size inference. Then actually you get a much more powerful result. You identify many more regions across the brain, which to be significant. So we really recommend using this higher threshold. And you can maybe understand that why. And basically, if you use a lower threshold, then you're incorporating information from some of the noise areas. The lower test statistics are not so interesting, whereas the higher test statistics, that's where really there's activation being interesting happening. So to conclude, TFCE, as classically used, has inflated voxel-wise and cluster error rates. We've introduced an approach which provably controls cluster-wise error rates and regional error rates, which means that it allows for increases in both power and localization. TFCE is not threshold-free, as it quite strongly depends on a threshold. And actually, the default choice of H0 equals 0 means that TFCE borrows information from all across the brain, meaning that it can make only quite a weak global statement. For localized cluster enhancement, we instead recommend a threshold of H0 equals 3.1, which is actually in line with the default for cluster size inference. So the slides for this talk are available on my website if you're interested. We have code to implement it in my StatBrains package. If you're interested in hearing more, Then there's further details that are available at my poster, which is 1871. Thank you very much.
Thank you very much, Samuel. Do we have any questions from the audience? Okay, I have one question from the app. Dr. Samuel, do you recommend the TFCE over random field theory approaches? And more generally, what are the differences?
Great question. So, yes, well, it depends which random field theory approach you mean. So some of the classically used random field theory approaches, they have inflated error rates as well, but of a different kind, even worse. Some of my work has looked at improving that and fixing some of the random field theory approaches, but as classically used, I wouldn't recommend them. So TFCE always uses permutation testing. It has a certain guarantee in that sense, but as I say, it doesn't localize the activation. So if you want to localize the activation, we recommend this modification.
Okay, thank you very much.
Thank you.
Okay.